Hi, so hello everyone. Welcome to the quantum sensing session. This session will have three great speakers, Angela Gamuras, Kirk Madison, and Shabir Brazen-Jay. Their research will cover different aspects of quantum sensing from experimental to theoretical point of view. You can ask questions through the Woover app and on the Q&A section. So to start with, we will start with Dr. Angela Gamuras. Angela, you can start sharing your slides and I will just introduce you. So Angela is a research officer in the Metrology Research Center at the NRC, where she is responsible for Canada's primary scale realization of optical power and spectral irradiance. She has been developing efforts in the few photon metrology and standards, and she's also adjunct professor at the University of Ottawa and fellow of the NRC U Ottawa Joint Center for Extreme Photonics. So Angela, the floor is yours.
Great, thank you. You can hear me and see my slides, hopefully.
Yes.
Perfect. Thanks so much for the introduction. Also, thanks so much for having me here today. So I'm happy to tell everybody about some of the work that we're doing at the National Research Council of Canada, specifically in the Metrology Research Center at NRC. So this work that I'm presenting today is being done in collaboration with my colleague Jianwan Jin here at the NRC Metrology Research Center. And together we're working towards different metrology efforts and standards for quantum detectors and emitters. So first, I'll just tell you a bit about the Metrology Research Center here at NRC. So many of you are likely familiar with NRC as quite a large organization. So we're in the Metrology Research Center, which acts as the Canadian National Metrology Institute. So what does that mean? So that means that we're mandated to realize different SI base units for the International System of Units and also maintain primary national standards. And so I'm sure many of us are all familiar with the different SI units that are shown here. So we don't only just do that, we also look into different measurement methods and techniques for new and emerging technologies, which is what I'm more going to touch on in my talk today. So one thing that we get to do in the Metrology Research Center is represent Canada at the Bureau in Weights and Measures here in France. And so they provide, a basis for an international and national measurement system of standards that's traceable to the International System of Units or SI units. And so we interact a lot with different countries so that we have different measurement standards so that we can have a cohesive system, for industry and trade and so on. So today I'll talk to you about our efforts in Canada mostly, but working towards different quantum photonic standards. So there's different types of standards that exist. There's physical standards like different measurement devices, like for instance, detectors or sources, which I'll talk about today. And there's also documentary standards that can document different definitions or measurement techniques. But today I'm going to talk more about physical standards. So for the outline today, I'm going to tell you about, why do we care? Why do we need metrology for these quantum detectors and emitters? And then I'll tell you about some characterization techniques for single photon detectors. I'll also talk about performance metrics and characterization of single photon sources and how this is all coming together to work towards quantum photonic standards for Canadians. So I think, between the talks, Quantum Days this year and last year, many other events and so on, photons are pretty useful things. And we've seen in the last few years that they've been used for distribution of entanglement, for instance, and they can also be used in programmable quantum circuits. In this case, with squeeze states in a collaboration between Xanadu and the National Institute of Standards and Technology in the US. And there's many examples of using photons for qubit encoding, for quantum computation and information transfer. So one thing we can probably all agree on is that, photons are going to be really useful in upcoming quantum devices to transport information. So, it's really it's really important to make sure that that we know and we can characterize our photons and think about how we're measuring them. So a lot of these demonstrations that I just talked about happened in the lab. And as devices move from the laboratory to being deployed in the field, we really need to make sure that they're stable and reliable and well characterized. So similar to the infrastructure that we're all using right now, our internet and communications infrastructure, devices that are deployed in this infrastructure are very well characterized and have many standards. And there's a lot of work that goes to making sure that devices are interoperable as well. So if we think towards if we're ever going to have some sort of quantum internet or quantum network in Canada, we need to sort of think about having these types of standards in place so that we can make sure that we have a reliable network moving forward. So you can already buy commercial QKD systems, for example, from ID Quantique and Cubatech and Toshiba. And there's already work going into standards development from the European Telecommunications Standards Institute into characterizing components that goes into these commercial boxes. So moving forward, we really need to think about how this is going to expand into a national and international infrastructure. So what tools do we need to do this? It would be ideal if we had a single photon source where we could press a button and get a photon out on demand. And also if we knew the wavelength and so on, all these characteristics of this photon source. It would also be useful if we had an ideal single photon detector that we knew how many photons we were detecting at a single time, for example. So first I'll talk about single photon detectors. So there's a few different kinds of detectors. There's a set of detectors that can be referred to as no-click detectors or digital detectors. So these encompass photomultiplier tubes, single photon avalanche diodes or SPADs, and also superconducting nanowire single photon detectors or SNSPDs. So these types of detectors will give you a click if you have one photon that hits the active area or several. So, depending on your application, maybe this is fine, but depending on what you want to do, you might want to have some photon number resolution. So there are different types of detectors that can provide that. There are transition edge sensor detectors that operate at extremely low temperatures and generally utilize a dilution refrigerator or an adiabatic demagnetization refrigerator. For those of you that may be familiar with the cryogenics to run these, they also typically have very slow recovery times, which can make them difficult to use for certain applications. Another method that can be used is either spatial or temporally multiplexed SNSPDs to enable photon number resolutions for certain measurements. Other considerations when you do want to pick detectors are, of course, the spectral range. You want to think about your photon energy, for example, and also if you have free space or fiber coupled detectors. Since fiber coupled detectors and fiber coupling generally introduces losses in the connectors and coupling light into the fiber itself. Other things we want to consider are the detector recovery time, the timing jitter, and so on and so forth is listed here. But today I'm going to talk more about measuring detection efficiency of our single photon detectors. So there's two popular methods for doing that. There's the calibrated photodetector substitution method of calibration, and there's also the correlated photon method of single photon detector calibration. So at NRC, here's an apparatus that we have in the lab to characterize single photon detectors using a substitution technique. Here we have an 850 nanometer laser diode that we use in this apparatus. And the idea here is that we have two neutral density filters, as well as a calibrated photodetector that's been calibrated traceable to the SI system of units. And we also have our detector under test, or single photon detector. So this detector that's been calibrated traceable to our SI system of units, or transfer standard detector, it's been calibrated in the microwatt range. And so we need to reduce the optical power down to a femtowatt range for our single photon detector. So what we end up doing is we use two neutral density filters, And so first we measure our light on our reference standard detector with one ND filter, and then the next, we put both of our filters in place in the optical path, move our translation stage over, and then measure our signal on our detector under test, our SPAD. So this reference detector is important because it goes up what we call a calibration chain. So we calibrate our transfer standard detector against our absolute cryogenic radiometer, which is our absolute standard in optical power measurement. So the idea here is that the cryogenic radiometer is a type of electrical substitution radiometer, which is calibrated traceable to electrical units. And so in this cartoon, it shows a bit how it works, where we have a really black radiation absorber, which absorbs our optical radiation. If we open our shutter, our optical radiation hits our absorber, and the instant radiant power is actually measured by determining the amount of electrical power required to cause the same heating effect on this absorber as an instant amount of radiation. So essentially we have a temperature sensor, so we can measure how much the temperature changes when our optical radiation hits this cavity. If we close the light, then we have this heater that applies the same amount of heat, which is an electrical substitution technique. So here we can actually go up our calibration chain, and we're traceable to our SI system of units this way. Here's another cartoon of our setup at NRC, where we have broadband light sources, a double monochromator system that gives us a single optical path. And we have our cryogenic radiometer in our system here. It's operating at 4K to minimize noise. And we have a flexible bellows system, so we can have one optical path, and we can measure our light with our cryogenic radiometer or with our transfer standard detector. So one major challenge with calibrating SPAD detectors is that their active area is very, very small, about 150 microns or so. And so we actually have a three-dimensional stage for the detector under test that actively aligns the detector to the center position on the active area. So here you can see a spatial uniformity map of this detector under test, for example. And so it's important to consider your spot size of these detectors so that you're underfilling them, you're not missing any photons. At the National Institute of Standards and Technology in the US National Metrology Institute, they have a similar calibration system to us, but it's mostly fiber-based. So this was built by Thomas Garretts at NIST. And so they also use a fiber-coupled laser, but they use variable fiber attenuators instead of ND filters to reduce the laser power in this case. They can also switch between a fiber-coupled scheme, which you can see here, and a free space scheme in their setup. So one study that Thomas Garretts did was he looked at connectorized measurements in fiber-coupled detectors. So especially thinking ahead to a quantum internet and actually physically linked repeaters and so on and so forth. The fiber optic connections can be very problematic. And so for instance, looking at some efficiency measurements of an SNSPD, he found that using a fiber connector versus using a direct splice gave a difference in efficiency of about 4%, which is not too bad depending on what you're doing, but this can also vary a lot more. So we actually compared the setups at NIST and NRC by measuring the same SPAD, the same detector under test at each setup and comparing them. So our comparison data is shown here. One advantage of the NIST setup that uses the variable fiber attenuators is that they can more easily get to lower photon fluxes, where one challenge of the free space arrangement that we have here is that we're relying on our particular type of reference standard, which relies on a transimpedance amplifier, which is a bit noisy at the lower photon fluxes. So even though we have a bit of our noisy data at the lower side, our comparison does agree within a 95% confidence interval. So this is one example of how National Metrology Institute would compare different measurements, so that if then these types of detectors were characterized in different countries and bought and sold between different areas, the client or consumer or person in the lab knows that they're measuring the same thing. The second type of characterization technique that I mentioned is the correlated photon method. So this method has its advantages where it can characterize the efficiency of your setup and not just the detector. However, you do require two different single photon detectors to accomplish this. So this relies on counting coincidences between two photons produced in parametric down conversion in a nonlinear crystal. A few years ago, Sergei Polyakov and Alan Migdal at NIST did a comparison measuring between this type of calibration with the correlation method and a substitution technique shown here. And they found that they had the same measurement result with very similar uncertainties by characterizing the detectors by either substitution or correlation. So performing calibrations using the correlated method is generally a lot more difficult because you do need to consider the losses in your optics. However, this type of method could be useful moving forward in an integrated circuit type configuration. So for single photon sources, that's sort of the second thing we want in our toolbox for our metrological standards. And so there's two main types of sources. There's the probabilistic sources that can be based on parametric down conversion or four-way mixing, for example. And there's also on-demand single photon sources that are generally solid state, which can be based on quantum dots, for instance, or doped nanodiamond, and also on different 2D materials, such as hexagonal boron nitride and TMDs and so on and so forth. So a lot of work has gone into the development of these types of devices, mainly for quantum information and also for performing quantum enhanced measurements and sensing applications. But on the metrology side, from a Metrology Institute standpoint, we're also interested in looking at these types of sources to redefine the unit of the candela into possibly a quantum candela based on a photon number, for example. So one big challenge in this field is measuring performance metrics and understanding what that means and how they're measured. So it's quite difficult in the literature to figure out who is measuring what and how, and if it's consistent. So for instance, the efficiency of your source and your G2 or your single photon purity, sometimes they're measured depending on what lab you're in different configurations with different optical filters or so on and so forth. And so one thing that a lot of national metrology institutes are working on now is developing different measurement vocabulary and procedures to try to unify this to make it easier to decipher and understand these types of characteristics. Another thing that has been mentioned in the literature a couple of years ago was measuring single photon purity, or G2, using photon number resolving detectors or click-no-click detectors. So it's been shown that, for instance, in this particular paper, the G2 measurement of a quantum dot was pretty different using a photon number resolving detector and with a click-no-click detector. So this is one thing that we want to work on as well moving forward, is understanding how to best measure these types of sources. So speaking of Canadian standards and work at NRC, one thing that we're working on, as well as collaborating with others at NRC who have been working on single photon sources. So there's a group also here at NRC, but in different research centers with Robin Williams, Dan Dalaku, and Philip Poole, and many others that are working on that team. They've been developing quantum dot nanowire-based single photon sources for some time for quantum information applications. So in the Metrology Research Center, we're interested in taking this Canadian solution to see if we can use it for a Canadian single photon source and standard. So we have our own setup here where we can metrologically characterize one of these quantum dot nanowire samples traceable to the SI system of units, and also work towards working with our international collaborators for coming to for developing common vocabulary and measurement techniques. So this approach has already been shown with different types of quantum dot structures in Germany. So the German National Metrology Institute, PTB, has used a similar setup where they also have a cryostat, and these are optically pumped quantum dots. But however, instead of the design that has been taken at NRC that have site-selected quantum dots, here they have quantum dots that they have characterized using photoluminescence and then deposited a Bragg mirror on top. And they were actually able to characterize this source in an SI traceable fashion and then calibrate a single photon detector with this source. So we're excited to use our Canadian developed technologies and work towards this type of implementation. So in our toolbox, we'd like to have our single photon source that's on demand and also our single photon detector that's well characterized, because then we can put some device under test in the middle and characterize it completely so we can deploy it in our infrastructure. So looking forward, the one thing we're also trying to do is look forward to on-chip integration with how this can be developed, again, for future technologies. And so we're thinking about how with on-chip with detectors and emitters, we can think about putting on different parts of, like, different types of optical components to essentially think of calibrating chips on site, thinking of different infrastructures. There's different demonstrations here of sources and detectors put on chip. And one thing we want to think about is how we can really characterize these in situ without having to remove components and replace them once this infrastructure for quantum internet and so on exists. So in summary, we talked about why we care about characterizing our quantum sources and detectors. We really want to be ready and think about making sure Canada's on the map in terms of quantum infrastructure and standards. So I told you a bit about how we can characterize these things and also how we can characterize and how we think about single photon source characterization and how these are all useful for Canadian quantum photonic standards. And thank you very much.
Okay, great. Thank you very much for your interesting talk. So I will start. You can ask questions for the audience can ask questions in the Wova app. I will start with one question. So you mentioned at 4K, you work at 4K, sorry, to minimize noise. What is really the noise figure? Is it 4K? And if so, would you gain sensitivity or lower noise if you would go to milli-K temperature, say in a DIL fridge? Or would it be like too complicated to do the whole setup in a dilution fridge?
I guess it depends what specific detector you're referring. It depends on the material. If it's referring to the cryogenic radiometer measurement, that's happening at 4 Kelvin due to the superconducting wire. I don't have off the top of my head what the material is, but depending on the temperature, the transition temperature that's used. And for instance, for the TES detectors, those require really, really low temperature. Those are not very noisy. I guess, I don't know if I'm being directed at the question, but I guess it depends what source and detector you're referring to. For the solid state sources, I don't think, like with phonons and the quantum dots and so on, I don't think going lower than 4K is very helpful. But I don't see any reason why you couldn't. Just the cryogenics and systems behind that are usually quite cumbersome and expensive.
Okay, great, thank you. Maybe I will ask another question myself. So it was really interesting, like the definition of the G2 measurements and the difference between the two measurement techniques that shows different G2. What is this? Maybe I missed, but what is this difference due to between the click detector and the PNR detector?
With the click no click detector, we could be you get the same signal regardless of how many photons are incident on your detector. So you could be getting more than one photon.
I see. Okay, maybe ask just one last question. So you showed some quantum dots that would emit photons, but it seems they would be embedded in some. It was in nanowires, but on the other experiments, it seems it was like on a slab. How do you compensate for the loss? I guess you have loss of photons going into the propagating modes because you have a very flat interface. Do you compensate for this?
Depending on the type of quantum dot and structure, it depends. So like the structures that I showed from the German National Metrology Institute do have a Bragg reflector inside to make the emission more directional. And the NRC quantum dots are already in this wave-guided nanowire structure. And so they have other work that shows proper coupling and very efficient coupling on chip as well. So there is some loss, but they do get enough photons out in one direction with the wave-guided structure that it works very well.
Okay, great. Well, thank you very much. I guess we'll have to switch to the next speaker. You can still ask questions in the Wova app, and then the speakers will be able to answer afterwards. So thank you, Angela. The next speaker is Kirk Madison. So I will introduce himself while he puts his slides on the go. So Kirk is an associate professor in the Department of Physics and Astronomy at the University of British Columbia. He received his PhD from University of Texas at Austin in the group of Mark Raisin, studying quantum transport using laser-cooled atoms trapped in optical crystals. He then did a postdoc at the École Normale Supérieure in Paris in the group of Jean Dalibard, studying quantum vortices in atomic Bose-Einstein condensates. Madison then did another postdoc in the group of Todd Dittmar at the University of Texas at Austin and Lawrence Livermore National Lab, performing tabletop nuclear fusion experiments by irradiating deuterium nanodroplets with ultra-short pulse lasers. Now at UBC, Madison's research group is focused on realizing quantum materials and quantum sensors using laser-cooled atoms. And today he will be speaking about new class of quantum sensors for absolute pressure and flux measurements in vacuum. Up to you.
Great. Thank you so much, Eva, for this introduction. I'd also like to thank the organizers for inviting me to share this story of this new quantum sensor. I'm having a little bit of a technical difficulty whenever I...
Yeah, you're not in the slideshow mode.
Oh, okay.
Yeah, okay, it's correct. Yeah.
Yeah. So when the technical difficulty is that my mouse, my arrow has disappeared from my screen. So I don't see it now. So I can't gesture. Anyway.
Okay. No, you're in the full slideshow mode.
Okay. You can't see my cursor, can you?
Move it. Can you move it or?
Yeah, I'm moving it. Yeah, it's okay.
No.
So I'll have to. I can only talk then. I can't gesture. So again, thank you so much for the introduction. Today I'll be telling you about a quantum sensor that we've developed for vacuum metrology. The work I'll be presenting is done in collaboration with Roman Krems at UBC, Dr. James Booth at BCIT in the Department of Physics, and Pinri Shin. He's on the far left. He's a PhD student in my group who's now moved to Quantum Valley Ideas Lab, working on another kind of quantum sensor using Rydberg atoms. I'd also like to acknowledge the National Institutes of Standards and Technology in the US. James Fedchak has been very helpful in this work. And I'd also like to acknowledge funding from CFAR in the very beginning, the Peter Wall Institute for Advanced Studies, and also funding support from the Canada Foundation for Innovation and NSERC. So, so let me begin by saying a few things about atomic sensors. As you all know, we now have atomic clocks, and atomic clocks are used for the time and frequency standards. And of course, you know, atomic clocks are used now and not quartz oscillators and whatnot because they have they're a quantum of matter, and they have a quantum advantage. And in particular, you can make an atomic clock better than any classical clock that you could possibly make. And there's been a lot of talk today and throughout this conference about quantum advantage in the context of quantum computing and quantum communications. But I think it's also important to acknowledge that quantum sensors also, they profit from this quantum advantage. So what might be one way of looking at the quantum advantage? Maybe this is very somewhat prosaic, but atoms, of course, are immutable natural objects. The sensors never age. There's no fabrication errors. No calibration is necessary in many cases. And this means that they are superior to any classical sensor you could ever build. And since atomic clocks were made, there's been a lot of research done on realizing other kinds of sensors. There are accelerometers and gravitometers now using atom interferometers. People make magnetometers with atoms, broadband EM wave sensors using rubric detectors, and quantum transducers. So this bottom left image I stole from one of Shabir Barzenjei's papers. He'll be talking to you next about quantum illumination. But he has done work on quantum transducers and using atoms in that case. So the work I'll be telling you about is making a quantum vacuum sensor, sorry, a vacuum sensor using cold atoms. So let me begin by, or let me say a few things about why we should care about vacuum metrology. And there are two applications that I'd like to highlight. One is device fabrication, and another one is aerospace. So we've heard a lot so far in this conference about the importance of thin films for quantum materials research and quantum devices research. These thin films are also important for high-speed transistors and devices which are ubiquitous in your cell phones and in your computers and whatnot. And these are by and large made by epitaxial growth methods like molecular beam epitaxy and ultra-high chemical vapor deposition. So what I'm showing on the x-axis here is sort of pressure, and these bars represent the pressures at which these fabrication methods are done or operated. And what's important to say is that in order to get good fabrication, you have to not only measure the pressure, but control it in the high vacuum and ultra high vacuum regime. In the context of aerospace, it turns out that understanding drag on satellites in very low Earth orbit requires that you know the pressure at those altitudes. And the pressures can vary many orders of magnitude. And so this is another instance where having good pressure metrology helps. There are, of course, standard methods for vacuum metrology. At the top left, you can see there's a mercury manometer. This is, is the pressure standard, classical pressure standard that's been used since vacuum was first invented. If you want to measure the pressure in the high vacuum and ultra high vacuum regime, or the extreme high vacuum regime, you need an ionization gauge. And gauges, like residual gas analyzers and standard ion gauges, what they do is they molecules or atoms which migrate into the sensor volume get ionized by an electron plasma, and then these ions are collected as a current, and that current is proportional to the pressure. Now, in order, these ionization gauges they require calibration because you don't know the probability of ionization is not unity and the probability of detection is not unity. And so you have to calibrate them. And so the way they are calibrated today is by using an orifice flow standard. So an orifice flow standard is basically a transfer standard that transfers or extends the range of a mercury manometer. And the main limitations of the orifice flow standard are that it's not a primary standard, it's not a standalone, it's a transfer standard. But more importantly, it is limited in the pressures that you can measure, and it is limited to inert gases only. So you can only calibrate an ion gauge for something like argon or helium or maybe nitrogen, but you can't calibrate an ion gauge while they are used in molecular beam epitaxy. You can't calibrate it for a flux of aluminum atoms or germanium. So any species which is reactive or sticky, you can't calibrate an ion gauge, at least not right now. And that's because the orifice flow standard is limited. Let me explain why that is. So this I'm showing here, I can't mouse around to indicate it, but on the right, what you see is a chamber at pressure P1, and there's mass flow into this chamber labeled by Q. That's coming from a flow meter, which is referenced to a mercury manometer. This mass flow then flows through an orifice, a hole of conductance C, and the pressure P1 can be related. It's simply the ratio of the mass flow Q over C with a correction factor that has to do with the pressure ratio P1 over P2, but that's a constant for all pressures in the molecular flow regime. So basically, NIST uses this. In fact, all metrology groups worldwide use this method to calibrate ionization gauges. And you can see on the right, there's a gauge being calibrated. It's connected to this pressure cell, and you create a pressure of known. You create a known pressure P1, and you measure the gauge response, and that allows you to calibrate the gauge. So clearly, if this mass flow which is coming in is a sticky gas, the flow rate out of the flow meter, it will not necessarily be the flow rate through the conductance hole to the orifice. In particular, if the gas is sticking to the walls, all bets are off. The pressure P1 is related to, but not uniquely determined by the flow rate Q in, because you can't relate it with respect to the conductance. If all the gas sticks to the walls, you have no idea what P1 is. So this means that you can only calibrate gases which are basically non-reactive, non-sticky, and only inert gases. NIST only calibrates for argon and nitrogen at this point. So let me tell you how you could solve this problem using an atom. And so I'm going to tell you about, or let's first talk about what might be the evidence of an incident particle on a sensor atom. And naturally, you would think, oh, you just look for a collision-induced state change of the sensor atom. So you prepare the atom in some internal state, either certain state population, or perhaps you make a superposition of internal states, and you look for a decoherence or a change of the internal state due to collisions. And this is well known in atomic clocks. It's called a clock shift. Whenever you generate the superposition to interrogate the atom for use as a clock, if there are collisions, it will induce a shift of the frequency. So people have known about this for quite some time. It is difficult to quantitatively get a pressure from a clock shift, but in principle, it should be possible. What I'm going to be telling you about is using the external state. So we prepare the atom at a very well-defined momentum. In fact, the momentum is 0 or very close to it. We cool to very near absolute 0. And then we look for a change in that momentum due to the collision. So we're using the momentum recoil. Now, of course, both of these methods require knowing and preparing and being able to read out the atom's state. We're using the external state because it's the most convenient for us. So if I have an incident flux or an incident flux coming from a beam or coming from all directions, if it's a uniform pressure, there's a flux density, which is the density in of atom of these molecules or these objects that are incident on the atom, and the flux is in times v bar, where v bar is the average velocity. And so the sensor atom presents a target for this flux of cross-section sigma, and the collision rate for the atom is simply in sigma v. So it's very simple. You just measure the rate of these collisions, gamma, and then you invert this equation and solve for n. So n is simply the collision rate, gamma, divided by the cross-section, the product of the cross-section and velocity, averaged over the velocity distribution of these incident particles. So that's the basic idea. Now, in practice, the collision rate, the single atom collision rate, can be quite small. In the UHV regime, it can be on the order of a second. You can think of it as like for molecular epitaxy, it's like a monolayer formation rate, and typically those are a second to 10 seconds. So you have to hold the particles so they don't wander off and leave. You have to hold them in a trap in order to get long interrogation times. So on the left, I'm showing a cartoon picture of an incident particle in purple hitting some sensor atoms in red. And on the right, I'm showing an actual picture of a cloud of lithium atoms in a magneto-optic trap. So if you just look at the particle number in the trap as a function of time, it will decay exponentially. And the decay exponent, gamma, is the collision rate. And in general, of course, your background vapor will consist of multiple species. So gamma will be a sum over all the collisions occurring for all the different species. And so, yeah, I'll talk more about that in a second. So one caveat here is that because we're holding the atoms in a trap, not every collision will generate particle loss, because, well, the trap has some finite depth, and if the particle gets hit but doesn't get hit, if it's hit gently, it won't leave the trap. So let me illustrate what I mean by this. So what I'm showing here is gamma is a function in argon, the density of argon. So the top equation shows you so I'm plotting gamma, the loss rate, single particle loss rate on the y-axis. And on the x-axis, I'm plotting the density of argon gas introduced into the vacuum system. So gamma, little gamma, is the sum of all the loss rates. So I can write that as gamma 0, that's the loss rate due to all the other stuff, plus the density of the argon gas I'm introducing times the sigma V, average of sigma V for argon rubidium collisions. In this case, the sensor atom was a rubidium atom. And the slope of this line of gamma versus in argon is simply sigma V. Now, for a shallow trap, the slope is quite large, and for a deep trap, it's not as large. And that's because not every collision is generating loss. And we can, we can refer to the slope, or the slope tells you the, let's call it the loss cross section. So instead of the total cross section, it is the cross section for collisions that actually generate loss from a trap. So if we plot this loss cross section as a function of trap depth, then what you see is this blue line here. So the open circles and the filled squares are data. The blue line represents the results of quantum scattering calculation. And what I'm plotting here is the loss cross section, sigma V loss, on the y-axis as a function of trap depth on the x-axis. And now notice the trap depth here this is a logarithmic scale. The far left is 100 microkelvin, and the far right is 10 Kelvin. So room temperature is way off to the right, okay? And what you see is that the loss cross-section approaches the total cross-section in the limit of 0 trap depth. But remarkably, so you might ask, when does the loss cross-section equal the total cross-section? Well, evidently, at least on the scale of our error bars, those two numbers are indistinguishable at trap depths about 100 microkelvin. And in particular, if you notice, the loss cross-section is half that of the total cross-section at a trap depth of about 20 millikelvin. Okay. So first of all, this tells you that in order to use atoms as a pressure sensor for room temperature collisions, you need laser cooling, because you need to be able to prepare the atoms in a momentum state which is small compared to the energies imparted in the collision in order to actually see the collision happen. And furthermore, you see that there's this there's this energy scale at which, in this case, which is around 20 millikelvin, at which the loss cross-section is half the total cross-section. So what does this mean? This means that half of the collisions that are occurring due to a room temperature argon atom hitting a rubidium atom, half of those collisions are imparting less than 20 millikelvin of energy. That's 10,000 times less energy than the incident particle has. So you might wonder, what is this energy? Well, and it's got nothing to do with the temperature, by the way, of the background particle. So this energy, which is shown in bottom left, is so-called quantum diffractive energy. So let me tell you what this is and provide some kind of hopefully some kind of intuition about this. So this quantum diffractive energy scale is Planck's constant squared over the mass of the sensor atom and the collision cross section. So it's h bar squared over a mass times a length squared. And you'll notice that it doesn't care. It only cares about the mass of the sensor atom, and it only cares about the total cross section. So so one way to think about this is that the sensor atom initially is delocalized in space because it has we've laser cooled these atoms. They're a delta function of momentum, and so they're moving extremely slowly, and they have a very uncertain position. Now, when a collision occurs, this incident particle, if it collides with the sensor atom, it finds the sensor atom in some volume, subtended by sigma, the cross section. So the post-collision probability distribution you can think of, this is a cartoon, of course, is like a cylinder whose cross-sectional area is sigma. And the result of this is that you've collapsed the wave function to a smaller volume. And due to complementarity, the momentum distribution must be wider. And the characteristic energy, which is just say p squared over 2m, is this confinement energy. It's h bar squared over mass times this cross section. Another way to say this is that this is the energy this is the 0 point energy of putting a sensor particle into a box of length root sigma. So this UD, this quantum diffractive energy, you can think of as a natural result of the quantum measurement produced by the collision. So in 2010, we filed a provisional patent using these ideas to quantitatively measure density using loss rate. So the idea, again, is you measure the loss rate and you know sigma v, and you solve for density. And now, in order for this to work, you have to know sigma v. So there are a number of ways of knowing it. And in this proposal, in this patent, we said, yeah, you could calculate it from first principles, or you could calibrate it using a known density. So if you know the density n, you can measure the loss rate of your atoms, and now you know sigma v, and you know it forever more, right? It's the calibration doesn't drift. That's the magic of this quantum sensor. There is another way, and that other way is a major breakthrough that we've had recently that I'm going to tell you about at the end of this talk. So in 2012 and 2013, I went around to some metrology groups worldwide, and tried to convince them that they should be measuring pressures in this way. And of course, the selling points are that you have an unchanging universal, you have a process which is unchanging universal based on fundamental atomic constants. It provides a true measure of the flux and pressure, and it works for any collision species, unlike the orifice flow standard. But there's a fly in the ointment, okay? And the criticism at the time was, well, you can't know sigma v, and you can't know it because the potential energy surfaces between your sensor atom and the thing hitting it are not good enough, And this is the proverbial many-body quantum problem that you can't solve efficiently on a classical computer. You have a many-body, many electron system, an atom with many electrons hit by a molecule with many electrons, and good luck trying to solve that problem. Solve the potential energy surface with any kind of accuracy. So the sense was you couldn't do this from first principles. And following this, a number of groups worldwide did experiments, kind of proof of principle experiments, but there were certain limitations to these experiments. No one did any ab initio calculations of potential energy surfaces. They didn't account for trap depth effects, and there was really not a good agreement with other methods of measuring pressure. So in 2017, NIST finally got funding to build their own UHV sensor, atom-based sensor, and they claimed that they were going to do an ab initio calculation for a simple system, lithium hit by hydrogen. It's the simplest possible sensor atom and target if you are incident particle, if you discount the noble gases that you could do. And they argued they could get a 5% uncertainty. In 2019, they did the calculation, and this has not yet been confirmed, but they have now a potential energy surface. And they argued they could use this calculation and bootstrap it using the orifice flow system to calibrate for other gases. So it turns out that this criticism is important, but we found a way around it. Okay, and the punchline is this: the total cross section can actually be obtained empirically, and we measure it, or we obtain it from measurements of the loss rate versus trap depth. So no calculations are required. So this works for any species as long as it's sufficiently polarizable, and I'll talk about that a bit more. So what does this mean, or where does this come from? So remember this curve I showed you before? If I now plot the loss rate gamma as a function of u and divide it by gamma at 0 trap depth, so I plot the normalized loss rate, that's equal to the sigma v loss divided by sigma v total. Okay, so I'm showing the same curve, and the assertion is that the shape of that curve, the shape of this curve of gamma u over u0, gamma naught, as a function of u, that's a universal function. It's independent of the short range physics, and it encodes the total cross section. So this work was published in 2019 in the New Journal of Physics, and then we used this idea to realize for the first time a universal quantum pressure standard. So it's universal in the sense of the collision universality, but it's also universal in the sense that it works for any species. And so what I'm showing on the right are data taken for many different species. So carbon dioxide, nitrogen, hydrogen, argon, helium. And I'm plotting for each one of these measurements. I may have lost track of time. I'm plotting for each one of these measurements this normalized loss rate. Eva, are you going to tell me my time's up, or?
Yeah, it's up, and questions time is up too.
Okay. Okay.
So
Sorry.
if you can conclude, yeah.
The conclusion is that this sensor provided, we measured we calibrated in this calibrated ion gauge. This is the standard way of that groups compare or flow systems. They calibrate an ion gauge and check the comparison, and the calibrations agreed at the 0.1%, at the 0.5% level. So this confirms at least that this idea works for nitrogen, and we believe it's generally applicable to any species. So thank you so much for your attention.
Great. Thank you very much for the great talk. I'm afraid we have to move to the next speaker because the next session is right after.
Absolutely.
But people can ask questions in the Wova app if they want, and you can chat directly.
Okay.
Thank you very much. Okay, so next speaker is Dr. Brazenjay. So he has a strong background in the field of superconducting circuit QED that he obtained in the group of David DiVincenzo in Aachen. He received the Marie Slowodska-Curie Fellowship to work as a postdoctoral fellow in Johannes Fink's group to experimentally develop integrated electro and optomechanical devices, as well as superconducting circuits that operate in the quantum regime. He's pioneered scientific research in proposing the novel microwave optical photon conversion based on mechanical resonator as open new methods for coherently converting optical photons to microwave photons, and consequently implementing microwave optical quantum teleportation. It was one of the first to develop the notion of quantum radar sensor, and he proposed the prototype for microwave quantum illumination sensor. So Xavier, the floor is yours.
Yeah, thank you very much, Eva. I think you can see the screens, that's right? All
yeah,
good?
We can see you on the screens, all fine.
And the presentation, yeah, thank you very much. So I think the last kind of presentation before you're going to lunch is the microwave, kind of like application of microwave in quantum sensing. And I'll focus on the entanglement in principle that you can using it for resource, as a resource in quantum sensing application in principle. So we are a pretty new group, started about 2 years ago before the pandemic, and we slowly growing and working in a separated and different type of systems, mainly and specifically in superconducting systems, micromechanical structure, for example, and using the superconducting system, connecting them to optical system for photon conversion and entanglement generation, for example. Currently, we're also working on the full microwave structures, and we are in process of building Josephson parametric amplifiers, which we already have one in the lab, and we can measure the amplification, entanglement, and also disorder superconductor for traveling wave parametric amplifiers, which we are in process of fabricating them also in the lab. In a bit different structure, we just started working on magnonic system and patterning the magnonic structure, building photonic crystals out of them. And in a very far away from these topics, we have 2-3 people in the lab working on quantum sensing and imaging, more specifically developing the sensors, and optical coherence tomography, for example, it's a good example for this. But today, I will mainly discuss about the microwave domain, the frequency for the microwave domain. It's in the order of 10 gigahertz, which is way far from optical domain, which Angela talked about it. It's in the order of a few hundred terahertz, for example. And as usual for quantum sensors, you need to develop the source of the entanglement, for example, or the source that you can using it for quantum sensing application, and also the detection part, which is also important. So in this specific presentation today and talk, I'll just mainly focus on how you can generate entanglement in microwave domain and what would be the application of that, specifically, again, in microwave domain. Let's start with the first topic, generating entanglement. I'll show you how can you generate entanglement in microwave domain using two types of systems, and then moving to the quantum illumination topic. The system I'm very interested in, it's the optomechanical system, or the mechanical structure that I will explain in a moment. And that is quite interesting area. The main reason is, if you're just looking at this very interesting paper, they sketched this, or just brought all of this quantum systems exist almost, not almost of everything, but covering most of the topics, with the coherence time with respect to the energy or the frequency. As you see in the micro domain, we are hanging around gigahertz frequency, while the optical domain is it's in the order of a few hundred terahertz. Typically, this energy gap between the two frequencies, it's very difficult to fill, and that means the two range of frequencies we have, they are almost separated from each other, and we cannot easily bringing them together and making connection between the two frequencies. So mechanical system, it's acting as a bridge. At the same time, it can couple to the microwave systems, and the other way it can couple to microwave structure. That means you can use the mechanical system to convert information from microwave to optic, or generate, for example, entanglement between microwave and optic as well. So in my group, as I explained, we're working on the photonic crystal structures and optical domain systems, and developing superconducting qubits and microwave resonator, as well as electro-optomechanical structures to connecting the two very different worlds. So what is optomechanical structure? Optomechanical structure, it's something like this. You have two very high reflective mirrors. One of them is extremely reflective and very white. The light here is quite small here, and the weight of this, it's really the photons inside the cavity can interact with the mirror itself, and the mirror can start to vibrate in principle. So you call this optomechanical structure because you have optical photons here, and you have the mechanical system here. And when you have two mirrors close by, you can form a cavity for the photons that they can stuck inside the cavity. And that means the radiation of the photons inside the cavity can easily and more efficiently transfer to the mirror, and you can construct the interaction between optical photons and the mechanical system as well. If you go through the analysis, which I don't go through them, you can find the interaction between photons, which you can see it here, and phononic structure, or the vibration of the system. And as you're looking at this Hamiltonian is nothing more than F, the force you have, time X, the displacement of the mirror. So the photons can apply a specific type of force to the mechanical system, and it can generate a motion for the mirror itself. This is where the mechanical part kicks in, and the fact that we have two mirrors, we have the cavity. That's why we call the entire structure optomechanical cavity. So as you're looking at this Hamiltonian principle, this Hamiltonian is nonlinear, meaning that it's typically difficult to looking at the dynamic of the system, and typically you cannot solve the equations for to extract information in later time, for example, about photons and phonons. But theoretically, you can always expand the operators by driving the laser very strongly with the laser. You can just splitting the photons, the annihilation operator, for example, in a classical part, and also the fluctuation. If you replace back this A, this operator you have in the initial Hamiltonian, you can just split A dagger A into two parts, as you see here, and then you have the mechanical part also close by. Why this is important in a practical point of view? I have now the choice that I can pick up different combinations of photons and phonons by just controlling the probe I have in the system. The probe, don't forget, it's related to the part which I have in my the Hamiltonian, and typically is a very strong laser you can just have in your structure. And this very strong laser as a drive, it gives you the possibility to pick up different combinations of the in the Hamiltonian. For example, you can pick up the By driving the system properly, you can pick up combinations of A daggers and B, meaning that you create photons by destroy phonons, and the other way around, you create phonons by destroy photons in the system. This is possible, for example, by pumping the system at lower frequency, lower than the cavity resonant frequency, and you can create something which we call a beam splitter interaction. This kind of beam splitter interaction, I don't want to go through it, it can be used, for example, for photon conversion, which you can using it to convert information from optical domain to microwave domain using a mechanical system. In principle, what's the plan? The plan here is to using this type of structure, building two type of beam splitter interaction, and using this mechanical system to convert, for example, the incoming signal from microwave to optic or the other way. So if you're looking at the efficiency based on the cooperativity you have in the system, if you have a moderate type of cooperativity, let's say around 10, you're expecting to get 90% conversion efficiency from optical to microwave. But this is not so easy in reality. It can has a lot of application kind of difficulties that you have to face. And this is a kind of like samples we have developed, which you can see here. You have a microwave domain, you have a mechanical system in the middle, and you have an optical structure close by. So if you zoom in this area, you have a mechanical system as in the forms of a capacitor, and this capacitor is shared with the photonic crystal structure, which is also vibrating. At the mechanical modes, they are just hybridized, and you can use this for photon conversion between optical domain and microwave domain. But the other part of the Hamiltonian can also be used for the other purposes, and that is the parametric type interaction, meaning that by controlling the drive or the pump I have in the system, and now I can pick up different combinations of the Hamiltonian, and that is nothing more than parametric interaction, which can lead to amplification or generating entanglement between phonons and photons in the system, which can be a resource, for example, in quantum sensing. How do you do that? The way you generate entanglement between between the radiation, electromagnetic radiation mechanic, and then mapping that to electromagnetic radiation is kind of simple. The way you can do that, you have a mechanical system in one side, you connecting a cavity to this, similar to what I explained, and you constructing a beam split interaction. Now, if the mechanic couples the same time to another cavity, which has a beam split interaction, we have a combination of, parametric interaction, you have a combination of beam split interaction and parametric type interaction. And you can show this Hamiltonian can lead to something which we call generating entanglement between the cavity 1 and cavity 2. Because the first interaction generates entanglement, the other one just swaps the entanglement. That means the output of the cavities, they will be entangled in principle. This could have a lot of application. One of them, as I mentioned, you can use the parametric type interaction for amplification, or as theoretically proposed a few years back, you can use this for, sorry, for some reason. You can use that for generating entanglement between microwave and optic, or you can using it for quantum illumination purposes, which I will also explain. So let's go here and explain specifically what do we have. If you have two cavities, they are coupled with one mechanical system. This mechanical system can generate entanglement between the outputs of the microwave system or electromagnetic radiations we have coming out from the structure. They are fully entangled. To prove this, what do we need to do? First of all, we need to fabricate the sample. This is the real sample, which you can see it here. We have two microwave resonators here. Those microwave resonators are very similar to what you see here. We have two cavities, and then they're sharing a mechanical system right in the middle. The mechanical system here, it's a vibrating capacitor. This capacitor is just vibrating, and it's shared between the two microwave resonators. And typically the gap here is extremely small in the order of 60 nanometer, and smaller gap, larger capacitance. That means larger coupling that you can reach using this structure. If you put this system in a cryogenic system and very low temperature, let's say 7 millikelvin, and using the structure or the mechanical system to generate entanglement, you can looking at the propagating fields coming out from the structure, and you can measure entanglement at very low temperature, let's say 7 millikelvin. If you're looking at that and backing out the information at low temperature at around 7 millikelvin, you can prove the existence of entanglement using the mechanical structure. So to do this, we have to do the tomography here, meaning that we have the quadratures or the fields coming out from the system. We can measure the quadratures and we can construct the Wigner function as a very good source that indicates the existing of entanglement and two-mode squeezing in the structure. As you see here, the blue area is the Wigner function for the measured photons coming out from the structure, from the microwave resonators, which we can compare it with the vacuum. If this goes below vacuum, that's a good indication of having two-mode squeezing. And of course, the two-mode squeezing can lead to existing of entanglement, for example. This squeezing, we can control it with the phase. And when you flip the phase and sweeping the phase, in principle, you see the two-mode squeezing appears at a specific angle, which we reach around close to 4 dB squeezing in the system. To prove existing of entanglement between the microwave radiations, we have to calculate something which we call it Dwan inequality. And when you do that, and when this delta goes below 1, you can prove the radiation coming out of the system is fully entangled. So what I have done so far is just using a mechanical system in microwave domain to generate entanglement between the propagating radiations. Now we can use more or less the same system for some specific application, which is the topic of the quantum illumination. For quantum illumination, before starting and discussing more about entangled sources useful for quantum illumination type, let's refresh our knowledge about the radar, the standard illumination. In standard illumination, you have a signal source. You're just illuminating the signal, the signal to somewhere, and the light or the signal reflects back, and you measure the reflected signal. From that, you can extract information about the existing of a target in the region, and you can extract information about the reflectivity or the environmental noise, for example. In quantum illumination, the concept is a bit different. You're using the entanglement, the initial entanglement in the structure to boosting the sensitivity of the detector, for example. How do you do that? Just consider I have the same entangled source, which I explained. You have two microwave resonator, you have a mechanical system in the middle, and this mechanical system generates entanglement between the propagating microwave radiations. I call one of them idler, the other one signal. So I know when I'm looking at the two quadratures I have in the system or the output fields, they are entangled. They have a specific type of cross correlation, and this specific type of cross correlation helps to improve the sensitivity of this specific type of, let's say, sensor. How that works, you have a signal, you're sending the signal to an area which is suspected to have an object there or not. This object is fully immersed with the environmental noises and is very low reflective. And then you're keeping the idler in your pocket, and then you combine the reflected whatever signal from the area with your reference, let's say the idler, and then when you compare the two components, you can extract information about the existing of the target in the area. It is possible to show that the system is quite robust with respect to thermal noises. Beside the entanglement is fully gone. It can work in high temperature for low reflectivity objects, and when the decoherence can destroy the entanglement, but still you can show the initial entanglement in the system can improve the sensitivity of the sensor. How can I model this? If I just looking at the entanglement at the output of the system, you can construct the covariance matrices, which is a very good way to analyze this type of systems. The diagonal term of the current of this covariance matrix tells you how much photons do you have in the idler signal. The cross correlation is captured by the off-diagonal term here, which you can see it here. So cross correlation is something which gives you the, for example, the squeezing, which I explained a few minutes ago. So now I can come up with two hypotheses. If there is no target in the area, what happened? Only when you're just shining the signal to the area, nothing can come back, only noise comes back. But when you have a target there, but this target is extremely low reflective, let's say the reflectivity is kappa here, small portion of the signal reflects back but reflect back, but then you have a huge amount of noise added to this. This small portion of signal, it's enough to really recognize that there is it's a kind of object in the area and I can detect this. How can I do that? The covariance matrix now is just split it in two cases. I have hypothesis H0, which there was no target. That means there is no correlation in the system because I know my idler is not correlated with my signal. But under hypothesis H1, small portion of the correlation still can be captured, and that is enough to come up with the situation, and I can compare and distinguish these two hypotheses from each other, which is a binary situation, and I can solve the, the plan here is to really distinguish these two conditions. And if you just comparing these two results, you can see that quantum illumination, the red, it's the most strongest scenario you can come up compared to the classical one, and it gives you 6 dB improvement in theory, and it gives you better sensitivity compared to the best classical sensor that exists nowadays. How can we just implement this system? It's quite good. It's non-invasive because you can just using very low radiation. The resolution can be better than classical one, but the problem is there is no optimum receiver that can catch the 6 dB improvement, and there is no microwave quantum illumination exists. Why microwave? Because the microwave naturally has more noise compared to optic, and this is where the quantum illumination is really important because you can really distinguish the existing of target in a very noisy environment and when the signals are experience a lot of losses. So we tackled this problem. We're just using Josephson parametric converter, not mechanical system because of the stability condition and bandwidth. We just use Josephson parametric converter as an entangled source. We generated entanglement between the signal and idler, and then we send that to room temperature to probe a target at room temperature while keep the idler and perform the detection. The result was kind of like interesting. We just first of all looked at the entanglement generated between idler and signal. We verified the entanglements there, and then we calculated the SNRs and compared the result for the case of the classically correlated signal and compared the result with the current state with homodynamic. So we just, in reality, we don't have access to photodetector. That's the first thing. And then the idler exposed to loss and environmental noises. So we have done a kind of like calibration for the idler and compared the result to the homodynamic and heterodynamic measurement. In reality, what we have done, we also went to the situation which we have a target few meters away, for example, from the antenna, and look at the reflected signal from the system and compare the result with, again, the current state and thermal radiation. So note that in this very specific situation, we did not do any direct idler detection, and we had done a kind of idler calibration, which means that what we have done is a kind of simulation of the quantum illumination microwave domain, specifically when you compare the result with current state. So in this case, we showed there is kind of improvement compared to the current state, but definitely there is improvement compared to the classical radiation, which the cross correlation for classical radiation is way small. It's smaller than quantum radiation. So in conclusion, what did we learn here today is you can use quantum electromechanics to generate entanglement, for example, between microwave radiation, and you can use that for quantum illumination purposes, although there is still some challenges that we have to face and solve in reality. Thank you very much for your attention. As I mentioned, we are just a new group here in Canada and working on different topics, ranges from microwave to optical domain. If there is any question, I will be happy to answer.
Great. Thank you very much for this impressive talk. Actually, we do have one question. So it says, fantastic talk. For standard quantum computation ideas, decoherence and losses ruin all quantum advantage. However, here with your QI, you seem to still get advantages using entanglement, even with high level of loss. Can you comment a bit more about why you still get improvement, even in the limit of extreme losses?
Yes, that is exactly true. In case of quantum illumination, the initial entanglement is fully gone, but the cross correlation is the important thing. The cross correlation, which I explained, the off-diagonal term of the covariance matrix, is what can survive during this process, meaning that the noise is not correlated with your idler. That means you can reject whatever noise exists in the system by just looking at the cross correlation between reflected signal and also the idler, which you just kept it in your pocket and you didn't touch it in principle. So the main really point here is that cross correlation is enough to distinguish if existing target in the area or not. And this reducing the error between the possibility of H0 and H1, which we didn't have the target and we had the target in the region. So that is the entire point of the quantum illumination.
Okay, great. Thank you very much.
Thank you.
There is maybe time for just one more question.
I have to end the session. The next session has started. Sorry.
Okay. So you can there is one more question you can answer on the chat, and I would just like to thank all the speakers of the session. It was really great talk. Thank you, everyone, and bye.
Thank you.